So let's talk a little bit about the team project. So I'm hoping to assign by the end of this week, and usually there's going to be 4 per team. So in the poll, I have an option. If you prefer to work with someone, it might be because you have the same schedule or you work very well together, let me know. I don't guarantee that I will assign that. I'll try my best because there's a lot of students. So you can mention that in the poll. Okay, but I'll try to assign it by the end of this week or so. So the project deliverables are essentially 5 team presentations, and then there are team assignments. You can submit them on Canvas as normal, but if that's not convenient, you send it on Slack, email. I really don't care. Just make sure you do it. The assignment one is the poll. We already talked about that. Any questions about this? The teams, okay, I should also mention, for those of you online, obviously you'll meet online. Sometimes, if you want, you can meet in person, build something, but you don't have to. For those of you in person, I'm completely ambivalent, so you can meet on Zoom if you prefer. You can meet in person, but you will need to meet and work as a team in some fashion, and you will need to create a cadence of meeting regularly to make progress. Okay, so I'm just warning you, it'll be outside this class time because we don't have enough time. So the projects are a big part of the class, and that's how you will learn a lot from this class. So make sure you assign time to spend with your project. I don't expect it to be a huge amount of time, but I would say at least 1 or 2 hours a week is what I would recommend, in addition to what this is, okay? And it can change. Sometimes it could be very low, you don't have much to do. Sometimes you might have more to do. But if you're struggling or if your team's not working well together, please reach out to me. We'll talk. But one of the goals of this class is when you go work in the real world, you will not be just doing assignments. You will be working in a team to solve some real problems. So I want you to gain that experience and work through those conflicts and kind of understand how to work together, how to take advantage of the complementary skills and things like that to make progress. Okay? This is really where it comes from. Okay, the topics vary very widely. It can be lots of different things. I put a list of things here that I have found interesting. So we'll talk a little bit about things like solar cookers, which are very simple. It's a really simple way to understand things: solar water pasteurization, desalination, solar refrigeration, daylighting. We talked about it. Water heating, photovoltaics, optics and recycling. Optics for hybrid systems, which means you're generating heat and electricity from them, and can be many others that, often some students come with some background and some really interesting passion, and that's fantastic. So if you have something like that, put it on the poll. I have a place for you to say that, and we could try to form a team around that. Let me try to give you an example. Last year or 2 years ago, there was a team, and this was a Zoom. It was an IVC or RRT team. And there were 3 people, and one of them came with a very, very strong software engineering background, and she basically led the team to create kind of like an app that if you're a homeowner who has solar panels on their roof, they can use that to really very precisely monitor the production, not only in the past, but also in the future, based on the weather, the air quality, whatever it is. And it was quite cool because they actually implemented it, and they got some feedback from real users and so on. So I was quite impressed. That's it was not much to do with optics, but I was very excited about it. So it could be that far away as well. I'm just giving you as an example. Doesn't need to be any, but I will assign the topics. But if you have something that you're very excited about, please let me know. Okay. The other thing I would emphasize is that as engineers, we are always taught to look at things very, very in a very narrow scope. Right? We have to solve a particular problem. Okay, let's take an FFT and see if this is the frequency which beats with this, and okay, that's my problem. Let's try to put a filter and remove it. That's not what this class is about. I want you to really think more broadly. So we want to build something that people will use. So go ask your parents, okay, if I build this device, will you use it? And listen to them. Ask them. Okay, they'll say no. Ask them why. And try to understand it and solve that problem. That's a more interesting problem. That's what I mean, not only technology, okay? Cost, durability, storage, cultural factors, ease of use, time conditions. And we'll talk a little more about the business model. In fact, your very last presentation will deal with this as well. Yeah, okay. Then we talked about this. So let me very briefly go over the 5 presentations. So the first presentation is really a literature review. So you're going to pick a topic, or I'm going to assign a topic to you, and there's a focus area. You're going to do a deep dive into that focus area and figure out what people have done before. They may not have done anything in the exact area, but there will certainly be adjacencies. So we're going to talk about that. You'll discuss the pros, cons, comparisons, overview of existing technologies. Could be papers, could be companies, could be presentations, whatever. Okay, so that's a little bit of work that you're going to do as a team. So you have to learn how to divide the labor. It's another important skill for this class. You can't have one person do everything. There are 4 of you, so you got to make sure everybody pulls their weight. Then you're going to, from here, you're going to identify top 3 problems that you want to tackle. And then by the second presentation, you're going to propose solutions to those problems. Okay? So you'll be creative, you'll be bold, you'll take risks, but of course you'll be wary of physics, as you are all engineers or physicists. Then presentation 3 is really a technical deep dive into your innovation. So we are going very fast, as you can see. It's 1 month apart, roughly, right? Roughly in every month, you're moving the needle. You're making progress, building the case for your innovation. Technical details, maybe a wire grid model, some detailed simulations, analysis, whatnot. Depends on what you're doing, obviously, before Halloween. And then which leads to before Thanksgiving, you'll have a demo day. You might have built something, hopefully. You may not have built something. Not everybody builds stuff, so don't worry. But you could even just build a model or do a much deeper technical analysis. Okay? And the last presentation will be a business plan and commercialization plan, and we'll talk about what those things mean. So you'll get a chance to kind of experience going, again, roughly in the cadence of roughly once a month. You're really taking this idea of a problem, and hopefully by the end of the semester, you would have come up with some solution which could potentially be taken out into the real world. Okay, for the online students, you'll submit videos. Okay, I already mentioned all this. And yeah, all the instructions will also be on Canvas. So I already talked about the assignments. Let me see anything here I missed. Yeah, I mentioned if I say team, it's submit 1 file per team. Otherwise, individual submissions are required. Okay, I think I already said all this. The last thing is about the business canvas and commercialization. So we'll do something called a business canvas. This is something I did not know anything about. I learned a few years ago. Essentially, it's a practice which allows you to think about your innovation, that allows you to think about things that are beyond the technical aspect. So when you take an innovation to the real world, what are the things that you need to think about besides the technology? But it's really a worksheet. So we're going to do that in class all together. And then you're going to do it again to improve it. And then you'll also create, like a very short 90 seconds video pitch for your product demo. But this will be part of presentation 5. And we'll say more about this later. And there are a few sections, so there's some of you might already know, but as engineers, many of you may not be familiar with, so it's a good way to practice and kind of learn what these things are. What's the opportunity, go to market strategy, market industry analysis, all this stuff. I highlighted technical product description because that's something which you will all be experts at as your engineers, yeah. And I'll give you lots of resources along the way. And I should also mention, I have some experience in this, although I'm trained as an engineer, an applied physicist or an engineer. I've started several companies and failed and understood from them, so I can give you some feedback and some real-world experience along the way as well. I'm involved in several today, so I can also talk briefly about that. Okay, so before I jump into the next part of the group class, I just want to highlight this email. I got this email a couple of years ago from Garen, who took this class a few years before, and he actually got a patent from the class, and that was his patent. They built this, so I'm just giving you what to aspire to. So they actually built a device and like a solar cooker, and he wrote a patent, and he actually got a patent granted. So that was fantastic. It was great. So if you ever end up doing something like this, please let me know, because I would love to see this. Not everybody will do it, which is fine, no problem. But if you have any questions about patenting and so on, the University of Utah is a great place. We'll have some of those folks from the licensing and technology licensing office come talk to you as well. But there are lots of resources. So I have some experience with this. So if you have, please reach out to me if you're interested in any of this as well. Garen turned out to be a patent attorney, so it was much easier for him to do so. Okay, so before I jump into this, any questions about the logistics of the class? Anything online? No? Okay, then let's jump right in. So, so first I want to talk a little bit about why we want to think about optics for energy in the context of the developing world as well. Because, and there's a motivation to this, I'll come back to this. There is a really interesting overlap between solar resources with little access to infrastructure. So the regions that have huge amount of solar resources, it doesn't have to be the developing world. I was recently in Southwest Arizona with what do you call it? The Navajo reservation, although there's a better term for it. Obviously, they have very little infrastructure, very little electricity, water, and things like that. This huge solar resource, right? So there's this geographical overlap. So can we take advantage of that? The biomass resources are fast depleting. We all know this. We can have a huge impact. So there's a lot of people who don't have access to a lot of these technologies that we could potentially bring access to. And there is a large market opportunity that we don't really think about. So I just want to make a brief motivation. And the rest of the class, I want to talk really about thermodynamics. But to talk about thermodynamics, I want to pick the example of solar cookers. And the reason I want to pick solar cookers is because it's a very simple system. I like simple systems because it allows us to tease out the details. So let's do that for the next 15 minutes or so. I'll start with the simple video. I'm going to turn off the sound. Oops. So this is an example. Hard to turn out. There's an example of a commercial solar cooker. It's a little bit old, but basically you have like an evacuated tube that you can essentially put at the focus of a parabola. You heat it up, and the parabola rotates, and it allows you to do this. And many of you have probably seen this. If you're a hiker, you probably have used it, or if you use RVs and things like that. Okay? I want you to pay attention because I'm going to ask you a few questions about this. Yeah, so I'll let it play through. Some of it looks pretty good. Okay, I think that's basically all you need to see. So sometimes this also messes up my... Okay. So you can have different types of solar cookers, and we'll come back to that. Okay, I have a few questions. So you could build something like this, which many of you might have built in middle school. My daughter recently, not recently, a few years ago did this. Basically, you create a greenhouse, right? You have a box, well insulated, you allow sunlight to get in, you have some sort of container. It's a greenhouse because the longer wavelength light doesn't escape. So it gets recirculated, you build up the heat energy here, you can have a reflector to collect more light, and we'll talk more about these things. They're very simple, easy to use. Okay? You can have a panel cooker. This is nice because it folds. Easy to ship, transport, very simple, it's not a box. However, it is not very sturdy, can fly around, right? Not very. There's no insulation, all that. So those are the pros and cons. Now you can have this. This is more fancier version. It's a parabola. We all know from our math that the parabola has a focus. You take, and we'll talk more about this in a couple of weeks. You have parallel light coming down to a parabola. It gets focused to a point. And that's exactly what's happening. You point this to the sun being really far away, the rays of light are parallel, goes to the parabola, gets focused to the focus, where you put something you want to cook. Obviously, the larger you make the parabola, you collect more of the light. The power density here is very high. The temperature can be very, very high. You can reach that temperature much faster. However, this focus is very sensitive. The sun moves, you have to track it. This is, by the way, a manifestation of the second law of thermodynamics. We will try to understand this conceptually. Okay? It's kind of complex, and it's hard to maintain the temperature uniform, things like that. So now, I want you to take about 60 seconds. First of all, talk to your neighbor and brainstorm, maybe nearest neighbors if you want. Brainstorm, how would you improve these 3 types of cookers I just showed you? Okay, and on Zoom, you can do the same, but you put it on chat. Okay? I've given you many examples. I'm going to ask you, so I won't ask you to shout out, but I'll come and ask you. I'm going to go to the very back. We don't have much time, but any ideas? How would you improve it?
A big boy. Coatings? More
coatings?
Yeah,
coatings on the mirror?
Yeah. More.
Reflections? Okay, good.
It's going to be costly, I think.
Yeah, potentially, maybe. Not necessarily, but maybe. Any thoughts? Oh, for the one that's folding? Yeah, but then the problem is that then you have to ship it, right? Then it gets expensive to ship, yeah. Potentially, yeah. Potentially, yeah. It needs to be durable, but yeah, cheaper, yeah, that's good idea. I'm going to ask you guys. You have a big group. Any interesting thoughts? Oh, you took it. Okay, I'll come back here. Sorry. Yes.
You could have something track the sun.
Yes.
This one doesn't look like there's a rotating element, so bring that from the first thing we saw to have something more evenly cooked.
Oh, I see. Okay. Yeah. Good idea. Yeah, very good. Yeah. Tracking the sun is very important. We'll talk more about it. Yeah. This is a challenge. Yeah. Did you? Okay, in the interest of time, we should move on. Anyone has any crazy ideas? I heard some really good ones. Any interesting things before we move on? Anyone volunteer? Anything interesting? No? Yeah.
I'm going to brag on this guy's idea.
Sure.
There's we're talking about things moving, and it becomes kind of visually hard because the excess light would hit the person making the food.
Oh, yes.
That doesn't sound like very fun to any of us. So something about finding a way of condensing into more of a home setting where it would have walls and more structure.
Oh, great idea. Yeah, I haven't thought of this. Yeah, you'll get really hot. Yeah. Yeah, great. Yeah, fantastic. Yeah, Mohan.
We can just make an entire cone, something like almond shape. So there would be 2 points of focus.
Yes, that's right. Yeah.
All the heat will be and then they will display to, let's say,
To make it more uniform.
yeah.
Okay, yeah.
So all of the heat will go to a specific point, and
Yeah.
this point will disperse the heat to the rest of
Oh, I see. So you have some way to conduct the heat to keep it
Yeah.
more uniform. Okay, yeah, potentially, yeah. You'll need two foci. That's the real challenge, yeah, I suppose, yeah. Good, great. I also heard some really cool ideas, so good job. And also on Zoom, yeah, I heard that was cool. Unfortunately, we have to move on. So, but hopefully you'll, I'm sorry. I messed it up. I have to catch up here. But anyway, this is an example that you will do, but this is a very simple idea, right? But you will hopefully do this with more complex problems as part of your team. And we'll do more as we go along. Of course, you can do what's called a Fresnel lens cooker. In the old days, the TVs used to have a Fresnel lens. So this is an example from a YouTube where someone actually picked it up from the dump or something and then built a whole solar cooker. It's essentially free, right? So you can get this. And anyway. It has very similar problems with the sun tracking and so on. Sun tracking turns out to be a fairly important problem, but we'll talk more about it. Now let's try to, from this very simple example, let's try to gain some conceptual ideas of what are the heat principles that are important. And you will recognize that what we extract from this example can be applied to any heat engine. And almost every project that you're working on, unless it's like a purely software project, will be a heat engine that obeys the second law of thermodynamics. So whatever we're going to talk about here in the context of solar cookers can be extended to whatever that you're going to think about. First, the greenhouse effect. So we are very familiar with this. What does this mean? So if you have a container like this, you have light coming in, visible light, UV, some near infrared. You have something transparent up here that allows those photons to come in. Some of it escapes, some of it reflects off, but the longer wavelength photons can be trapped by this material. That's what a greenhouse effect is. It allows the short wavelength photons to come in, prevents the long wavelength photons from escaping. Typically, CO2 does that to our atmosphere. But we can do that with polymers, for instance, plexiglass, some types of glass and things like that, okay? Now, what does that mean? That means there is energy coming in, but not all energy is escaping. That means work is being done on the system. There's energy being input into the system. The consequence of that, from the first law of thermodynamics, is the temperature has to go up. Very simple idea. Happens here, happens to the planet. Now, of course, that by itself is not enough. That, excuse me, that energy that came in needs to be captured efficiently. That's why you need what's called a black body here. We'll talk about what that is. It absorbs those photons, thermal photons typically. Can be visible photons too. A black body, an ideal black body is a black hole, which doesn't exist in reality. But a realistic black body obeys what's called Planck's law, which we'll talk about later. It will absorb as many photons as its temperature allows. And it also emits. But again, you don't want it to lose energy. And that's what the design of this material is quite important. Okay, and then that energy that's absorbed by this black body needs to be conducted into whatever you're cooking or whatever you're doing with it. Doesn't need to be cooking. You could be generating electricity here. That's why I said everything is a heat engine. Could be a car. You're running a car, right? Doesn't really matter what's happening inside. Work, energy is coming into some system. Is doing something useful with it. That's a heat engine. Not technically, there's a bit more detail there, but now let's talk a little bit about the heat gain and the glass orientation. So I have two boxes here. One box. Another box, a little bit bigger, which will receive more sunlight. Not everybody shout out and answer. I'm just kidding, you can shout it out. But you have to explain why.
The surface of incident is perpendicular to the energy.
Exactly, yeah. So the important thing here is that we have to look at the incident power, right? So this is the surface that's collecting the light, but the light is coming at an angle. So the cosine, you have to project the rays that come here to this surface. The cosine, there's a cosine of theta. That will reduce the amount of energy that goes in here. Now, even if this length is the same as this length, which I should have said before, because it's oriented better, the cosine theta cos 0 is 1. You get most of the light. So you get more energy. This could be important for some situations where the light is, where the sun is moving. In all situations, the sun is moving. Which box has more losses? We haven't talked about losses. And what are the losses? We talked about some losses, but not. Anyone has any thoughts?
Assuming there's any reflection on box 1, there's a lot more reflective losses.
Some light escaping, you mean? Yeah. Why is this more than that?
Because you're assuming you have a sort of reflective surface passing through versus glancing off the surface of it. If there's multiple
I see. So you're saying that the angle of, you might be getting more reflections from the top surface because it's at an angle. Correct. And you can all do this. If you, actually you can't do it now, but you can do it later. If you look at a window straight on, you'll see very clearly. But if I go at an angle, you will see a reflection. It's exactly what he's talking about, right? This is important. Why is this important? So I don't want to lose that energy. I want to collect it. So I want to think about how to collect it later on. Anything else? Any other losses?
I think the other box, probably if they're both made of the same material.
Yeah, let's assume, yeah.
Let's assume they're made, for instance, cast iron or something. You have a higher heat capacity in the second one because you have more
material.
Yeah. To store heat in.
Yeah, that's a good point.
So
I didn't think of that. Yeah.
Storage.
Yeah, it'll take longer to heat it up, but it will maintain the heat. Yes.
Stop. You just have to give it off.
Right. That's not a loss, though. I would say that is a heat gain, probably. Yeah. But what is another loss? Where else I'm going to lose energy? Sure. Oh, there's nothing in there, so you can use it for anything. But let's assume you're cooking something. Yeah. Yeah. Yeah.
Maybe some of the heat is that it goes into the vessel itself
Yeah.
rather than being trapped inside. So I would consider this form of heat as well.
Yes, I agree. This would be an efficiency. So we would think about the efficiency of conversion from the input power, there's some power coming in, into some output work done. We'll talk about this later. And heat engines is called a Carnot cycle, Carnot efficiency. Yes.
There'd be an issue. You have more surface area.
Exactly. Yes. But why is that important? In fact, that was the answer I was looking for. Why? Why is this important? Let's stop here.
Well,
what does surface area have to do with this?
Thermal capacity,
yeah.
Everything else is given off, and you'll have larger surface.
Yes. The give off, this is the loss. Yeah, this is the loss I was looking for. It is giving off, which means it's radiating heat away. Yeah. You're going to radiate away the energy. This is radiative losses. What does that mean? You're a black body, all of you. You are all emitting light. You don't see it because it's in the infrared, 8 to 10 microns or so. Okay, we are all losing a light. Okay? That's exactly what happens here. So, and that is proportional to the area, surface area, by something called the Stefan-Boltzmann law. We'll talk about that. It depends on temperature and the area. So the surface area turns out to be very, very critical. Okay. That's just a quick note about the losses. Now, you can gain reflectors. Reflectors turn out to be quite important, and we'll talk more about this in the non-imaging aspect. But what happens by adding a reflector here? So I have one reflector here. You can see that the light's essentially bouncing off. If I don't have this reflector, these rays will simply escape the box. It will never enter it. By just adding that, I'm creating more energy that enters the box. By adding one more reflector on this side, I can get more. So I'm essentially increasing the effective aperture of collection.
You're just going to reach heat faster.
Exactly. Yes. I'll heat up everything faster. So this is a way to increase the effective light capture area, and this is what a solar concentrator does at the end of the day, and we will think about how to design this optimally. This turns out to be quite important. We'll come back to this example. How would you increase this gain? We're almost out of time, but I want you to take, let's say, 30 seconds. This gain, this slide, how would you improve this? Go ahead. Yeah, how would you increase it? I want to increase the gain even more than what I have shown on the right. Feel free to discuss. You only have 30 seconds, so you're out of time. So I improved it from here to here. What more can I do? What can I do?
Can use a spherical vessel, and that would concentrate the heat better.
I don't know.
I think so. Because
Why?
most, if it's a sphere, if it's a perfect sphere, all the light, all the heat will pass by the very center of the sphere. So like concentrating everything.
I'm not sure. I'm not convinced. I have to think about that. Anyone have any interesting answers to that question? No. Okay. I'm going to move on in the interest of time. So what are the loss mechanisms? We need to understand conduction, radiation, and convection. Radiation we talked about, but there's also losses that happen with induction, which means, for instance, heat that gets conducted out, the insulation is not perfect. Right? We are all familiar with this from your homes, in your AC and so on, right? It can be convection, where the molecules of air can take the heat away. Okay? This heating happens partly by convection because there are air molecules in here unless you put it in a vacuum, which is getting heated up, and then it touches the black body, transfers the heat, gets cooled, and moves around. Okay, so that's an example. So we have to be very thoughtful about how these things are designed. For instance, the absorber plate must be insulated from the bottom of the cooker. The radiant heat must be trapped by using the appropriate material on the top, and the heated air may leak through any gaps and things like that, which you want to fix. Yeah. So those are some simple examples. And then you mentioned heat storage. So the thermal mass is, of course, very important. If you have some material which can retain the heat more, like cast iron, for instance, or water. Water is a fantastic thermal mass, right? If you go to the ocean, the hottest time the ocean is the warmest is usually right after summer, because it's heated up all the way through summer. After the summer is when you really should go on your vacation, because the water is warmest, let's call it. But the higher thermal mass means it also takes a long time to heat up. So you have to be careful with the design there, and you should be aware of these things. You should also think about materials requirements. I'm hurrying through it because we're out of time. I won't say much, but except that it needs to be, you have to think about the structure of materials, whether it's, renewable, whether it can be inexpensive, can it be transported, insulation, transparent materials. So moisture resistance, of course, important if you're trying to do cooking, right? Because it's generating a lot of moisture, so you have to make sure it will last. There are many other design considerations which are independent of all of this. Size, what is the appropriate amount of food? Is it for a person? Is it for, if you're a hiker, for a family, for a village, whatever? Portability needs, cookware, accommodation, sunlight collection area. This is an interesting question. Is a square box better than a rectangular box? I'll let you think about this. I'll come back to that. And there are many other challenges for adoption, particular to the solar cooker. Taste of the food, right? Tastes bad, no one will use it. Temperature control, what about cloudy days? Cost. Disrupting traditional gender roles. It turned out to be one of the big challenges. And we can talk more about that. But the key thing I want you to understand is there's huge opportunities for technologists like yourselves to think about these sorts of problems, simple problems. But of course, there are first world problems too, because you can apply all of this to people who want to hike, people who want to be out on the ocean with your boats for a long period of time, on a camp, whatever, right? There's all kinds of opportunities out there. And with that, I will stop here because we're out of time. But I can answer questions if anyone has. So I'll wait a few minutes to see if there are any questions on Zoom. Are there any questions here? So I'll stop, but any questions? Not, I will see you all tomorrow. Okay, I will check the schedule, and if there is I will correct it, and if there are any big problems, I will make an announcement.
Oh, yeah.